Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be continuing our discussion on the second part of the continuum mechanics, and we were since the last module we were diving deeper into the structural form or the basis of determining the constitutive relation of the materials. So this is our continuum mechanics part 2, where we are going to primarily start with the form of the constitutive relation, how to essentially determine what are the properties, or how to pin down what are the properties of the constitutive relations that every relations must satisfy. So to do that, we have to look at the structural basis for constitutive law. The structural basis of the constitutive law, and we need to understand how structural changes in material during deformation affects the constitutive law. During deformation affects the constitutive law. Okay, a constitutive law. Now to do that, we have to go all the way down to the molecular level and see what are the various forces which are acting on these materials, which will lead to the constitutive relations which is sought after. So for example, the simplest case is that of the metals. So for metals, at the molecular level, we will have at the atomic level, we will have atoms which are arranged in lattices. So atoms arranged in lattices with its pairwise interaction given by some interaction laws. The common type of interaction laws could be that by the so-called Lennard-Jones. So the lattices with pairwise interacting force of the form F, given by alpha by r to the power m plus 1 minus beta by r to the power n plus 1, and we have that m is between. So this is how my powers are. The powers of these factors are all positive, and alpha and beta are positive constants. So we see that the first term in this potential represents an attractive force with a positive term, and the second one is a repulsive force with a negative term. Now if we were to find the potential to the problem, the potential, we have F, the force is given by dV dr. So my potential V when integrated will give us minus alpha times m by Rm plus beta times n by Rn. So this is my Lennard-Jones potential. This is the so-called very famous Lennard-Jones potential. So now we want to see what is the arrangement of the lattice, that is when there are no net forces acting on the system. So we want to see what happens at equilibrium. So at equilibrium, we have the net force must be 0. Net force F must be 0. If that is the case, we can plug this relation, this is equal to 0, and we can take our F is equal to 0. So we can take that set f equal to 0 to find that r naught, the distance or at equilibrium or no net force, the distance between the various atoms r naught comes out to be beta by alpha to the power 1 by n minus m. And where, so I call this r naught to be my equilibrium spacing. Equilibrium spacing, that is an optimal spacing when there are no net forces acting, right? So then if essentially we want to draw this force diagram, let's say force versus r, we see that the force is at r naught is going to be there will be an equilibrium spacing r naught, beyond which we have repulsion, and below which we have attraction, or below which we have repulsion and above which we have attraction. And if we were to draw the corresponding potential to this problem, we see that the potential will behave as if this is r naught. So at r naught we have the minimum potential. If we solve this potential problem, we see that at the point of equilibrium spacing, the potential becomes the minimum. So the minimum is the stable equilibrium, or this is the equilibrium of the system. Okay, so then let us say we typically want to find the stress acting on the lattice of these atoms. So how about the stress T, which we want to find? To do that, we need to pin down the cross-sectional area of this lattice. So we can say that in a cross-section, in a square cross-section, we have an area given by sigma, which is the area sigma is given by in a square cross section of area sigma, there exist sigma by r square, r naught square atoms. So there are these many atoms in the square cross section, right? And then, so from here I can derive that my total stress is sigma by r naught square by times f by sigma, right? Or we have the total stress is f by r naught square. So this is my stress which is approximately in terms of sigma for a square cross section. So now I am ready to write my constitutive relation. So again, we are assuming a linear constitutive relation. We have that the linear constitutive relation is T at r naught plus r minus r naught T prime at r naught. So this is assuming linear constitutive relation with Lagrangian strain. So this is r minus r naught by r naught. So this is nothing but E of ux, right? So from here I can find that my Young's modulus is 1 over r naught times df dr at r equal to r naught, right? So this is the net force. So this is my relation between the Young's modulus and the interatomic spacing. So if we plug in the formula for the force, we get that this is n minus m times alpha divided by r naught to the power m plus 3, and this is the relation between the Young's modulus, and the interatomic spacing, which is my r naught. The interatomic spacing, which is my r naught. Typically we keep m to be 6. The coefficient, if we go back, our coefficient m and n. So we keep m to be 6 and n to be 12. This is nothing but the so-called the Sutton-Chen potential, or sometimes also called as the Lennard-Jones potential. So for 6, 12, we also have the so-called Lennard-Jones potential, which is typically for inert gases. These are not for metals, but so this is an example when we take these values of M and N. These are for inert gases, and they represent not a very strong interactive forces, but they are typically van der Waals forces, relatively weak interaction forces. So van der Waals forces. Okay. So then I would like to discuss some restrictions in the constitutive laws. Some restrictions. So restrictions, I am trying to note down all the constraints that a constitutive law needs to satisfy, and for doing that, let us see what are the restrictions in the constitutive law. Okay. So we have a major, it turns out that the major problem in continuum mechanics is always finding the constitutive law for the material. When I say finding constitutive law, we are in a sense not talking about Newtonian material or material having simple linear stress-strain relationship. So we are essentially moving towards the discussion of non-Newtonian material. So major problem in continuum mechanics is finding appropriate constitutive law. Okay, so for example, if we have a hard material, we expect that there will be a small deformation. We have a small deformation, and the constitutive law can very well be approximated by a linear theory, right? And if we have a soft material, we will have a large deformation with strain, so we will need a nonlinear theory for soft material, or we will see the so-called viscoelastic material. So for example, rubber, for example, is typically a soft material, and we use a stress-strain relation of the following. So A epsilon plus B epsilon cube, where B epsilon cube is the nonlinear term. And then similarly, material like spider silk. For spider silk, we can use an even more nonlinear relation. For example, T is given to be A times e to the power B epsilon minus 1. So this is typically from the literature that I am quoting, from some standard viscoelastic literature. So then the first restriction that I would like to highlight for constitutive relation is that they should be relatively simple, and it should nicely describe the stress-strain data. So it should be simple and nicely describe the stress-strain data. And since the range of strain, remember, strain can be compressive or expansive. Since the range of strain is from -1 to infinity, our constitutive laws should faithfully represent the behavior under extreme conditions. So the constitutive laws should represent the right behavior under extreme conditions. So we have that epsilon goes to -1, or the material is compressed. That is, we should have that the epsilon goes to -1 when the material is compressed to 0. Compressed to 0. So this is one extreme condition that the stress-strain relation must exhibit. So then let us also talk about the concept of so-called frame indifference, because our constitutive relation should be frame invariant, as we shall see later on. So let me introduce the concept of frame indifference. Frame indifference. Right? So this question now is what variables, we are trying to answer this question, what variables can my stress T depend on that are consistent with the definition of stress. So that are consistent with the definition of stress. Okay. So what variables can my stress depend on? So to answer this question, let us talk about the so-called principle of material frame indifference. So principle of material frame indifference. Okay. So what this problem says, what this principle says, that the form of the constitutive law for stress should be independent of the observer, whether the observer is on the Eulerian frame or the Lagrangian frame. So the principle says that the form of the constitutive law, for stress should be independent of the observer. So this is one relation that my constitutive law must satisfy. So meaning, let us try to highlight this idea with an example. So suppose we have a two coordinate system, moving and a fixed frame. So suppose we have two coordinate system. So x star is x plus bt and my t star is t minus t naught. They are the two coordinate system are related as follows. Then my f of x comma t is frame indifferent. If my function f of x comma t is also equal to f of x star comma t star, that is, it is the same value in the different frames. That is for all initial times t naught and permitted values of the function bt. So now we allow the constitutive law to only depend on frame indifferent variables. We are going to only allow constitutive laws to depend on frame indifferent variables. Okay. So let us look at with an example what I mean by that. So for example, we have displacement is not going to be frame indifferent. Displacement is not frame indifferent. Why? Let us see. Is not frame indifferent. So suppose we have two frames. Let us say we have two frames, and the positions are x and x star, where my x is chi of x comma t and my x star is chi star at x comma t. Right? So now, so the relation between the two frames is given the change in coordinate, we expect that my x star is going to be x plus bt. So that was from the previous relation that x star is x plus bt. So now what we see is, so from here, so we expect b is non-zero. Otherwise, there is no point in discussing here, right? So now from here, we also get chi star is chi plus bt, that is in the material frame. So now in terms of displacement, we see that u star is equal to u plus bt, right? Or in the Eulerian frame, we have that u star is u plus bt. So capital U and small u, right? So now for frame indifference, what is the condition that we need? For frame indifference, we need to have that the displacement u star must be equal to u, or this is equivalent to saying that b of t must be identically equal to 0 from this relation here, and that is not possible because we have assumed that b is non-zero, right? So which means that the displacement is not frame indifferent. So certainly our constitutive relationship cannot purely include purely displacement. Okay, so similarly I can show that velocity is not frame indifferent. So frame indifferent. So velocity is not frame indifferent. How is that? Because again we use two frames of reference, x and x star. We have the displacement u star is u plus b. From here we can see v star is v star is equal to v plus b prime differentiating, and again we can see that v star is not equal to v because b prime, otherwise b prime will be because b prime is not 0 or b is not a constant, right? So that is the case here. So velocity is also not coming to our list of possible variables to be included in our stress strain relation. So what variables can be included in the stress strain relation? Notice that when we use the linear constitutive law T is equal to epsilon ux, can ux be used as a variable in stress strain relation or the constitutive relation? The answer is yes, because we will see that ux is frame indifferent. So the third example shows that the function ux is frame indifferent. How so? Because my u star at x comma t star is going to be u at x comma t plus b of t, and if we take the x derivative, then u star at x is equal to u at x, and my u at x is u at x by 1 plus u at x, and we see that in this case my u star x is u of x, right? So both the in both the coordinates u of x is identical. So then this question is, let us now note down what variables are frame indifferent, and all these can be separately checked. So frame indifferent variables. What are these variables? We will see that the variables such as density rho, or the material derivative of the density rho, or the material derivative of u, the displacement, or the Eulerian derivative of u, or the material derivative of the velocity, or the Eulerian derivative of the velocity. These are all frame indifferent variables and they can be individually checked. Now similarly, frame variables which are variables which are not frame indifferent, let me also write down some of them so that we try and avoid those variables in the constitutive relations. For example, the Eulerian derivative of the density, or variables such as displacement in the Lagrangian and the Eulerian frame, or the velocity in the Lagrangian and the Eulerian frame, which we just saw few minutes back. So which means that the conclusion is that the constitutive, so this is my conclusion so far, the constitutive relation must include frame indifferent material, frame indifferent variable. The constitutive relation I would say must use frame indifferent variables, and it could have a combination of many frame indifferent variables, right? So for example, we will see that in the case of viscoelastic material, which we will introduce in 2 modules later, in viscoelastic material, we see that the constitutive relation F comes out to be that stress is a function of ux, and both the displacement, derivative of the displacement and the derivative of the velocity, that we will see. So we have both the strain and the strain rate appearing in the constitutive relations for viscoelastic material, to be seen few modules later. And then I think let me now also start introducing what other conditions that we have to make sure that the constitutive relations must follow. So one of the another conditions that the constitutive relations must follow is the so-called the principle of dissipation, right? And to do that, we have to introduce the concepts of the so-called entropy, and also introduce some laws of thermodynamics to arrive at the principle of dissipation. Okay, so I stop my discussion at this point, and in the next module I will be introducing the principle of dissipation via the ideas of entropy and entropy density and the free energy. So thank you so far for listening. Thanks a lot.